So something nice about typing and answering each of you guys' greeting is that I can confirm, because I type using 注音, so I can confirm whether I'm reading your names correctly. Yeah, this is one of the benefits I discovered. I like your name, Jason. 深海. Yeah, you will probably be a good diver with a name like that. Sorry, I'm just teasing you guys. 云彤 and 14届剑物暑期营. Oh, shoot. Okay, did I type up everyone's name? Oh, no, and there's also Wei Xiang and Xuan Hao and everyone else. Okay, welcome back. All right, so the announcements today, let's see. Yeah, we have the regular lecture link, Google calling link, and the dues. PA number 2 will be doing. Quiz number 6 and 7 will be doing this week. Okay, so PA number 2 slightly harder than PA 1, and quiz number 6 and 7, the number is one less than last week, but it gets a little bit more complicated, particularly for quiz 6, which will be quiz 6 will be happening today. Okay. There's just one more announcement. Okay, so in case you guys, especially those who are auditing the class, okay, the account of students not officially, okay, registered for the class will be disabled. So on Slack, I see there are almost like 50 accounts. Okay, so we'll try to disable the students who actually tried to check the class out and decided to take other courses, or they have multiple classes they want to add and decided that, hey, if they get into another one, then they join that one. Okay, so hey, the first couple weeks, all I can say is just chaos. It's a chaos for you guys. It's also a chaos for the professors. So I will try to keep the Slack group a little bit simpler by disabling these accounts that are not registered students. So if you intend to audit, okay, and you wish to stay on Slack, please just send me a DM on Slack or email. Okay, I'll keep you on there. Okay, otherwise I'll just disable these other user accounts. The reason for this is because that at some point I need to post also the shared Google spreadsheet of your grades. All right, and I consider those private information. So we would wish that there are only the class knows about the grades and progress. Now, those who are serious following the course, of course, we probably don't mind just 1 or 2 extra people know. But it's better not that, random people joining the group get to see your grades, okay? All right, and let me just say hi to Xuehan and Jimmy and Sean, okay? Now we are gonna start the first topic. So last week, remember we had a quiz talking about contrasting circuit switch network versus packet switch network, right? So circuit switch network, the philosophy is more reservation, dedicated, no loss, no unpredictable delay. But packet switched, well, we try to utilize the resource whatever that's available. Okay, so no reservation. Whoever comes gets served. Okay, and whoever comes first gets served first. So you have better resource utilization. There's no idle, but you might have contention, and delay for indefinitely long. And worst case, you might have packet drops when there's not enough buffer space on the network. Okay, so trade-off. There's no slam dunk solution really. And from you guys' quiz solution there, I saw some of you saying that it depends. It does, isn't it? Although you prefer one way versus another, as students usually you prefer that it's cheaper and all of us can share. So I guess most of you prefer PS, packet switch network. Now, internet is a packet switch network. All right, so you guys' intuition are actually very close to how the rest of the world develop. You see, the majority opinion, okay, in a way shows how the economy actually drives the development of the engineered systems as well. So today, let's start from listening more about packet switch network. Because in the introduction of packet switch network, you hear a few keywords like store and forward, okay? That actually adds extra delay. And this store and forward thing is necessary, in fact, for the packets to traverse the network to the right destination. Okay. Another thing you might have heard is also that, hey, packet, right? We cut big file into packages, but packages are probably still too large. We cut them into packets, even smaller than packages. Okay, so that meant we tend to cut big files into small chunks. Okay, small packets. Okay, why small packets? All right. So these are the two things that this video will talk about. It's a little bit long, but Polly played a trick today. So I actually speed the video up by 1.25 times the normal speed. So Polly would appear talking faster, but it might be okay from a listener's point of view. Because I try to listen to my own video, I find that if I play 1.25 times, that is the perfect speed. Okay, it will not appear that the video is dragging, and in the meantime I can understand. So let's see how this video works out for you, and please do let me know whether this is too fast or too slow for you after the video. So this video about 10 minutes. The next few slides, they are still somewhat important, okay, but not strictly talking about packet switching, circuit switching, and the comparison. So these slides are to answer a couple important questions. We said that packet switching, what it does is to divide data stream into small packets. But why not large packages? Right? We didn't really justify that. We kind of like that L divided by R. The time it takes to send one packet is small because this is small. And in case the link is really fast, then this is small. But if this is a little bit larger, well, not so bad either, isn't it? Well, think again. And this is the example that I try to use to set up the stage. And it's just a slightly extended version of the previous example where we have 2 hops only, just one router between the source and destination. The packet size 7.5 megabits and the link rate 1.5 megabits per second. And you see that L divided by R is 5 seconds. And because there are 3 hops, so this time store 5 seconds, 4, store 5 seconds, 4, and 5 more seconds to store. Altogether, 15 seconds to send this packet L. Now, 7.5 megabits, large, right? Sending a large package like this over this 3-hop network, 15 seconds. Let's try dividing this large message into smaller packets and see how it will work. 7.5 megabits, let's divide them into 5,000 packets. This way, each packet is only this big, 1.5K. Link rate is still what? 1.5 megabits. So to send a small packet like this, it takes only 1 millisecond. Now, look at this. This is the same network, 3 hops. Each packet is now very small. And to send one packet, the first router will take 1 millisecond to receive it and then send it out. So 1 millisecond, 2 millisecond, and only 3 milliseconds until the destination receives the first packet. And you know what? These links can work in parallel, right? Because router 1 here can be passing packet 1 while the source start passing packet 2. You're trying to do also streamlining here, except that the unit of the streamlining is a small packet. You see, why packet switching suggests small packets? Because it's trying to maintain the benefit of doing circuit switching. Unfortunately, we could not be streamlining bits, okay? But let's keep the packet small. Then we get to keep some of these nice properties in a circuit switch network. And having these links that can work independently is nice. We can pipeline or streamline the sending of the packets over the network. So each link works in parallel. The overall delay in the end is what? 5002 milliseconds, only 5.002 seconds. If you recall earlier, if we send 5,000 small packets altogether, 7.5 megabits, each hop 5 seconds, and 3 hops 15 seconds. How much time are we saving? Big time, isn't it? This is why in packet switching, people always talk about cutting data into small packets. And why do we need to store packets first before forwarding it, right? This is one of the reasons that we still need to form packets. Why we cannot just streamline the bits. The reason has something to do with how the routers is working. So inside the router, there are 2 key functionalities, and there are 2 of these. First is routing. So there's some sort of algorithms there. The router's given the graph of the network, computes the shortest route. At the end of it, we generate a routing table like this, a forwarding table like this. And the way we look up this table is by matching the destination address, of the packet. And so if a packet comes into a router, inside the router takes the destination address in the packet and look up this table. If there's a matching entry, the router discover what is the next router to forward to, what is the right direction to pass this packet further. You see, router what? Oftentimes well connected to other routers on the internet. So this router here could have multiple ways of passing the packets further. Unlike the very simple scenario there, each router has only one outgoing link, right? So it's no longer that intuitive why packets need to be stored and then forward. Now you see, packets need to be stored here, and then the router can look up this field and match this entry and then discover, okay, this packet is supposed to go out on network interface 2, this direction, to this router next. Similarly, this router needs to store the packet entirely, and then it can look at the header, this particular field, destination address, and find out in its own routing table which router next to forward the packet. Yeah, it's exactly because of the forwarding functionality that's required to pass data around over a packet switch network like internet. So on packet switch network, we store packet before we forward it. So forwarding here is to move packets through routers all the way from the source, eventually reaching the destination. Right? We'll definitely tell you more as we come to chapter 5. Okay. So in datagram network or in data network, the way it works is let's receive a packet entirely, and look up the destination address to determine which is the next hop. And so you see, if the routing table changed, if the graph changed, routing table would change. When the routing table changed, when the forwarding table changed, the subsequent packets might be following a slightly different path to the destination. So the routes, packet traverse might change in a session, in a data stream session. So the analogy here is that packet switch network is a little bit more like the regular car network. If we are driving a car, a lot of times, to find out the next segment, which road segments we should go on, we might actually stop and pause and ask someone for this destination, for direction, or park to the side and then look up Google Map to find out which is the next segment. And actually, in a packet switch network such as internet, we can potentially emulate a circuit-like behavior that is called virtual circuit network. So instead of looking at the destination field in the packet header, we look at a very special header field called the virtual circuit ID field. Okay, so there's a tag there, carries a number. Okay, that number determines which is the next hop. So inside a packet, there could be many fields in the packet header. One is called destination. There's another one called the virtual circuit ID. And one can look up that field and decide which is the next hop. And how do we do that? We'll talk about that also in chapter 4 and chapter 5. And what's nice about this approach is that we can then try to ensure all the packets for that stream traverse a fixed path. In a way, packet number 1, 2, 3, 4, chances high that they arrive in order. In this case, in case routes might change, if the later route is shorter than the earlier route, chances there packet 1 might arrive after packet 2. So, packet switch network. To sum everything up, this is general communication network. 2 different flavors depending on which philosophy we design the core of the network. If we are going for a circuit core, it's called circuit switch network. If you're going for a packet-centric core, packet switch network. In circuit switch network, we know there are different ways of dividing resources into pieces. Frequency division or time division. But either way, it's very regular following certain order. Things will need to be reserved. There's a call setup delay. It's good for long-lasting calls where you will prefer data not experiencing variation in delay, not experiencing losses. But this is very resource consuming. Each time we will not be able to allow many users going on at the same time. On the other hand, packet switch network, simpler, flexible, no idle resource, but we might have congestion. So that's this track, datagram network. We look to the destination network address and then decide which is the next hop to forward. And so we need to store the entire packet, and so they might get queued, and they might get dropped in case there's not enough space in the queue. But we can also try to emulate a circuit behavior using the virtual circuit tag, which allow us to look up into the packet header field that's a little bit faster and streamline the process more or less and maintain packet arrive orders. Packet switching versus circuit switching.
So that was all about the core of the internet. Okay, so last week you heard about the edges, and then today we finished the core. Now, the rest of the video for chapter 1.3 is just this. Okay, if you recall at the beginning, the overview of chapter 1, we say that the internet is a network of networks. Okay, you see like a mini picture of the internet. This video next is to explain how come internet grows into a network of networks. There's a reason for it. Okay, so the next video, about 9 minutes, maybe slightly less than 9 minutes.
Internet structure. It's a network of networks. Earlier we learned we have end systems at the edge of the internet. They're connected to the core through the access networks, which are part of these access ISPs. Now, some of these ISPs serve home users more. They're called the residential ISPs. Others serve companies and universities. They are more often being called institutions and ISPs. Well, either way, any two hosts in these ISPs wanting to send packets to each other, their access ISPs will need to be interconnected. As a result, we see a network of access networks. Over time, they grow pretty large and complex. And much of these growth is driven by the economics, and some of it driven by governmental or business policies.
in the next few slides, what you'll be seeing is essentially the evolution of the internet. What I'm drawing here is a bunch of these access ISPs, or I call access nets here on this figure. Let me just omit drawing the end systems because there's just going to be too much of them and the picture gets too messy. So the first thing the internet engineers are thinking is this: how are we going to interconnect these guys? Well, one obvious way is, how about connecting them all? But as a result, you see there are n square connections. And when the internet grows, adding one more access net, we'll need to add n extra links. So this is going to be a very expensive thing to maintain. And so internet engineers go with the other extreme. Everyone connects to one global ISP in the middle. So data come here, and the global ISP transits the data for the access net to the destination. Similarly, here. So in a way, the global ISP in the middle here is providing transit services to the access nets, which are the customers. Now, as the internet grows, as the number of these access nets grow, then there will be more paying for the transit services. Gradually, the global ISP will begin to see profit. And when business is profitable, you see competitors. So now we have not just one global ISP, but multiple global ISPs. So A, B, C here are 3 global ISPs. They're competitors, but unfortunately they also need to collaborate. Because what? Just like the access nets needs to be interconnected so that they can serve the end systems, their customers. ISP A, B, C will also need to interconnect so that they serve their customers, the access nets. All right, so must interconnect. There are 2 ways for the global ISPs to interconnect. First is to establish peering links among each other. The other is to connect through these IXPs, Internet Exchange Points. Now these IXPs are special. They're typically set up by government fund or by the nonprofit organizations because it's kind of important that we have these, third company there maintaining the basic operation of the internet to avoid companies, commercial companies, to dominate. So that's pretty much the structure of the internet for a long time. But over time, we see more. So local communities such as this guy and this guy here can also grow. When there's enough number of these access nets around, we begin to see regional ISPs show up. What these regional ISP is doing is this: offering lower price internet access to the access nets and try to negotiate internet access with the global ISP with a lower price. So hopefully the regional net here finds a margin of profit. So profit here and saving money here. For global ISP, this might not be a bad thing at all because it only needs to deal with one customer, which is the regional ISP, instead of multiple of them. Okay. So less overhead. And this structure has been there for a long time until about a decade ago. Content provider networks showed up. Let me talk about content provider network by example. So let me use Google here. It'll be easier for you to understand. So Google established these data centers worldwide. What they do is to go to access networks locally where the data centers are, and then ask to connect to the access network, their data center. Now, the number of machines they're maintaining there at their data center and the connections they're buying from the local ISP are actually comparable to the global ISP here. The entire infrastructure there at the content provider network is just as big as the global ISPs in the middle. But what's a bit odd is this. The content provider networks, they're actually physically at the lower level of the hierarchy. As opposed to the global ISPs, they are at the center of the hierarchy. Scale comparable, but where they are in the hierarchy, very different. All right. In the next picture, let me try to draw the network slightly differently so that you see where they are in terms of how resourceful these provider networks are. You see here then, the most resourceful one at the top, the least resourceful one at the bottom. So at the center, we have Tier 1 ISP and content provider network. Tier 1 ISP interconnect to each other through peering link, and they also connect to the IXPs. Content provider network somewhat different. They connect to the local access ISPs and IXP. All right. But keep in mind, this is not exactly absolute. Some Tier 1 ISPs might also have access ISPs connections. Google here, if this Tier 1 ISP offers a fair price, might also establish a connection. All right, good. Now, the final slide is just to give you a rough idea what's inside a Tier 1 ISP. As I'm drawing here, it looks simple, but it's actually quite complicated. This is a Sprint's backbone. Sprint is one of the major operators in the US. It's also a Tier 1 ISP. Each of these red dots is called a POP, point of presence. So the role there is pretty much like a data center in Google. It's a rack of machines. In this case, a rack of routers. Okay, so rack of these routers. They're interconnected between each other, and they are also offering connections to the customers. And some of them might be connected to other Tier 1 ISPs. And these links are to go further up into the backbone, in the hierarchy of the backbone in Sprint's network. And this is internet structure, a network of networks.
All right, so the videos are actually faster than the previous videos, right? Do you guys like it or not? If you actually find it okay, just say okay. Those who say fast, could you type up on the chat saying a little bit too fast? Okay, so you have 5 seconds to do that. 1, 2, 3, 4, 5. Okay, so I guess not much. Okay, so I see Xiang saying okay. All right, good to know. Very good to know. So I was a little bit worried that it might be a little bit too fast. I'm not quite sure if you catch the stuff I want to talk about. Okay, but let's go on for a few more videos like this in case you feel strongly about the speed of the video. We will turn back, but unless I hear from you that you feel strongly about the speed of the video. Okay. Next, we're gonna start a new subchapter 1.4. It's talking about the performance of the internet. Okay. So as you see, internet it's a network of networks. Okay. There's a structure there. It seems that there's a hierarchy there. But as you see in the previous video, it's actually a little bit chaotic. It's loosely hierarchical, no longer strictly hierarchical, right? ISP up there and access network down here. Right? It gets a little bit complex. Okay, there's no strict level 1, level 2, level 3 network. Okay, so having a messy network like this, okay. Implementing protocols on it and seeing it work is not particularly challenging. What makes it challenging is can you sort of optimize the protocol, revise the design such that it works, not only works, but also works well. Okay, so next there's a short video talking about how do we quantify performing well. So there are a number of metrics. And here they are. Starting from here, we'll focus our discussion mainly on the packet-switched internet. And 1.4 is to talk about the important metrics we care about designing protocols for it.
That includes delay, loss, and something called throughput, which we'll talk about at the very end of 1.4. How do loss and delay occur? Well, let me draw your attention to the example below. That'll be easier. First kind of delay is happening here in the packet that is going out, being transmitted out. That delay the packet is experiencing is called the transmission delay. That is the time it takes to transmit the packet, and we know how to calculate, don't we? It's packet size divided by the link rate. But there's a second kind of delay experienced by packets here before they get to go out. These are what? Packets waiting in a queue, waiting for its turn. And how can there be packets waiting in a queue? It actually happens quite often when the incoming rate exceeds the outgoing rate. So you see in the example, A and B sending packets actively together into the router. In case the aggregated arrival rate is higher than the outgoing rate here, then you will see there will be always packet here waiting to be transmitted, and therefore subsequent packets will need to what? Wait up. And that is queuing delay these packets are experiencing. Now the calculation of queuing delay is a lot more challenging than the transmission delay. It really depends on the arrival pattern before a packet comes into the queue. Okay, now if that pattern is reoccurring, predictable, then it will be easier to calculate this. Otherwise, very challenging. Now, that explains packet delays, where they might occur. Packet might get lost as well at the router, and it happens here. Focus on this thing here. It's the packet queue. The size of the packet queue is limited. Okay. By the way, that packet queue is also often referred to as the buffer. Okay, and the buffer space is limited, just like the memory space is limited. The buffer space is just a way of calling the memory reserved, okay, to store these packets. Now, given that the amount is limited, in case congestion persists for a long time, then eventually you run into the situation. There's no longer free buffer space in the queue. In that case, arriving packets will get dropped, and therefore we see packet losses.
All right. And next, let's talk a little bit more about delay. But let me try to address the question. Guan Yu was asking something about the ISPs, because we had a video showing that the internet is a messy network of networks. So Guan Yu was asking, okay, does it mean that they might use different algorithms, okay, such as datagram VCs, datagram and VC also in one of the videos earlier? Is there exist a rule for them to use the same algorithm due to convenience? This is a very good question. Okay, they do use different algorithms or strategies to transmit data, but within that ISP. Okay, they do have control because the routers, okay, these days, these routers are actually form the core of the ISP, and most of the traffic actually traverse through the routers. So how these core routers inside an ISP transmitting data, that can be an algorithm that the ISP chooses for its purpose. Okay, but between the ISPs, okay, so data eventually after coming out of an ISP, it needs to go to another ISP. Okay, so between the ISPs, so at the higher level, at the global level, in order for these ISPs to be able to send data back and forth between each other, they have to agree on a same algorithm or same way of routing packets. Okay, that is not exactly for convenience, but it's more for consistency, for reliability, for correctness, in fact. Okay, so that algorithm that every ISPs rely on to transmit data from ISP to ISP is in fact not exactly efficient. Okay, We'll talk a lot more about what you were asking in Chapter 5, the routing algorithms. Each ISP can choose their own within the ISP. Between ISPs, they have to use the same one, okay, in order to make sure that data go from one place to other reliably. All right. Next video, delay. And after this video, we'll have quiz number 6. Now, depending on how much time this video takes, we might actually start tomorrow with quiz number 6. Okay, so let's talk a little bit more about delay, one of the 3 metrics, okay, that we just talked about in the metrics overview video.
Now, packet delay. There are 4 components. The first component is the Nodal processing delay, but we just call it processing delay. It occurs right here when the packet arrives at the router. Router here checks the bit errors in case there's any, and decides quickly which output link the packet should go out. Next, queuing delay. That's the time the packet waits until it's turn to go out on the output link. It occurs right here at the buffer space where packet queued up. But the amount of wait depends on the congestion level of the router. Component 3 is the transmission delay, and it's calculated this way. R being the link bandwidth, L being the packet length. And the time to transmit the packet out will be L divided by R. And it's happening right here at the interface between the router and the link. Final component, propagation delay. Provided the length of the physical link and the propagation speed of signals traveling the physical link, we know that the propagation delay is D divided by S. So essentially, the time for the packet to traverse the physical link. Be careful. S here is the distance the signal can travel per second. R here is the number of bits the transmitter can push out per second. Although I call S the propagation speed, R the link speed sometime, but there are 2 very different quantities. Right? Now let's go through a couple examples to exercise calculating transmission delay and propagation delay. What you're seeing here is a caravan of 10 cars. Now the way to think of this scenario is this. Think of cars being bits and caravans being a packet. So we have a packet containing 10 bits in a sense. The cars will be propagating at the speed of 100 kilometers per hour over 100 kilometers, reaching the second boost. Toll boost number 1 here takes 12 seconds to service the car. All right. Question here is asking how long until the packet is lined up before the second router. Alright, so transmission speed, transmission delay plus the propagation delay. So what is the transmission delay? We have 12 seconds serving per bit, and then there are 10 bits. So the time to push the entire caravan out of the toll booth is 2 minutes. And then the propagation delay is for the car to travel 100 kilometers. So 100 kilometers dividing the propagation speed. So we have 60 minutes here. And so altogether, 62 minutes before the entire caravan to reach the second toll booth. So you see, in this case, transmission speed very fast, propagation speed slow. In the second example, the configuration is slightly different, mainly propagation speed and transmission speed. Propagation speed now goes really fast, but transmission speed much slower. So question here is asking, will the first car arrive at the second toll booth before all the cars are being serviced? Let's see, when will the first car arrive at the second toll booth? So transmission delay 1 minute, propagation delay. So we have 100 kilometers, but we're traveling 1,000 kilometers, so we'll be spending 1/10 of an hour propagating, and that's 6 minutes. Together, 7 minutes. So the first car will spend 7 minutes before arriving at the second toll booth. Now, 7 minutes is also the time to service 7 cars for the first toll booth. That means we have 3 cars that are still behind at the first toll booth. So yes, okay, when the first bit arrive at the next router, there could still be bits not yet transmitted out from the previous router. So in this case, where the propagation speed is really fast, transmission rate very low, you had this weird situation. Good. Let's sum up packet delay. So there are 4 components: processing delay, queuing delay, transmission delay, and propagation delay. Transmission delay, very low, typically microseconds. We just ignore the processing delay when we calculate packet delay. Transmission delay, propagation delay, very easy to calculate. L divided by R, this quantity is often significant and especially the case for low speed links. Propagation delay, slightly harder. It varies quite a bit from microseconds to hundreds of milliseconds. So this extreme is for satellite links, for example. We've seen earlier, it could go up to 200 or even more milliseconds. Sometimes the transatlantic or trans-Pacific links, very long optic fibers, could also take up to 100 milliseconds. Now, in the process of calculating packet delay, the hardest component is this, queuing delay. Now, it's very hard to calculate accurately because it depends on the congestion level at the router. Just to give you a sip of how hard it is, let's define again, R being the link bandwidth, L being the packet size. Let's add one more variable, the average arrival rate. So L multiply A is the average bit arrival rate. That is also the incoming traffic rate. R is the outgoing traffic rate. So we could define traffic intensity being LA divided by R. So when that quantity is close to 0, that means incoming rate very low, outgoing rate very high. Then no bits really need to wait. So queuing delay very small. And it's depicted here. When LA divided by R is very small, queuing delay also very small. The other extreme is here. When the intensity is greater than 1, that means there are more bits coming in than more bits going out. And when time goes on and on and on, the newly arrival bits will need to wait longer and longer and longer. And it's pretty much here, approaching infinity. Now, when the intensity is between very small to 1, delay is simply growing. And as we will be approaching infinity, you see that the curve grows quickly like that, okay? Close to an exponential trend. So, hard to estimate queuing delay. In fact, it takes a whole semester for a professor to teach about how one calculates queuing delay. And at the graduate school, there's advanced queuing delay that one can also take to make sure that you do a better job, okay? Estimating queuing delay for highly dynamic incoming traffic. All right. So that was the theory part of the packet delay. One can also find out what is the real internet packet delay by trying out this program, traceroute. Okay. What it does is to measure delay from a source, one hop at a time, all the way to a destination. So this is what I'm drawing here, source to destination, and it's sending 3 packets, one at a time, to reach each of the routers along the way. So router there receiving such a packet would return by sending a reply back to the sender. Now the sender there can time the interval between the transmission and receiving the reply and gets one estimation of the round trip time between the sender to the router. So it works like this: 3 probes to the first router, 3 round trip time estimation. 3 probes to the second router, 3 round trip time estimations to the second router. And this goes on and on until it reaches the final destination, and then the traceroute program stops. The output of the program looks like this. This is an example. Trace routing from Gaia, UMass.edu to Oracom, France. So this is saying first hop router's name is CS-GW at IP address 128.something.something.something. And there are 3 round trip time estimations, 1 and 2 milliseconds respectively. What's a little bit interesting is between hop 7 and 8. There. You see at hop 7, round trip time was about 22 milliseconds, but suddenly to hop 8, the delay is about 100 milliseconds. So that is the transatlantic links connecting from US to Europe. A little bit more interesting is also hop 17 and 18. You see stars. That means the routers are not responding. Okay? And it could be because the probing messages are lost or the replying messages are lost. but it's more likely that the router is turned off replying to these, routers are on, but the routers turn off replying these probing messages. Well, let's try, sending a trace route ourselves from here. How about that? Let's go over to a terminal and then trace route to say Google. How about that? All right. Good. First hop router. Well, it didn't tell me the name of the router, so chances high that the router doesn't have a name. Okay. Delay reasonable. 10 millisecond, 3 millisecond, and another 3 millisecond. Router 2 here, well, either the probing messages are lost or router turns off the functionality of returning to trace route probes. Now third hop, 30 milliseconds, suddenly much higher. Okay, fifth hop, delay not much higher than the third hop. And you see here, when it's star, it takes longer time. It's because when the traceroute program sends the probing packet, there's a timeout interval. Traceroute will wait until the time exceeds the interval. Then it determines that, hey, the router is probably not going to respond anymore. So forget about the first probe, send the next probe. Next probe waits also some amount of time. Timeout, give up, and then sends the third probe. Okay, good. Finally, we reached www.google.com. But the name is actually quite different. TSA something something. Interesting. And the end-to-end delay, end-to-end round-trip delay to www.google.com is about 20-something milliseconds. Now, something that's very odd is here. Hop 8. If you look closer, we do have 3 round-trip time estimates. But each time, number A here along the way, the 8th hop, is slightly different. IP address is 101, 49, and 97. So you see here, packets, although going to the same destination, coming from the same source, as they go on the internet, the routes could actually change. Also, you see, hey, the time it takes to reach hop 5, 30 milliseconds, but the time it takes to reach hop 12 is only 20-something seconds. So the load of the internet changes also over time. So sometimes when you are probing to a closer router, it could take a longer time because it was busier there. But when the traffic load drops and when you're probing a router that are farther away, you could get a shorter round-trip delay. Very curious. And let's go back to the slide. And it turned out that it's a good time to start the next quiz.
All right, so this is the quiz. There's not going to be enough time for you guys to work in a team to come up with the solutions. So we'll continue this tomorrow morning. Okay, so make sure that you tune in tomorrow morning to try to address these questions. So this is the traceroute result to oilcom.fr, just like on the sides. Okay. Q1 is asking, how come the 3 delay measurements are not quite the same? Okay, so if you pay attention to the video, you'll know why, right? Q2, how come some delay measurements to hop number 10 are longer than those to hop number 11? Hop number 10, right, along the route should be before hop 11, but delay to hop 10 can be longer to hop 11. How come? Why? If you don't recall, go back to that video again that I just showed you. There is a reason why hop 10's delay can sometimes be longer than the round-trip delay to hop 11. Q3. Q3 is a trick question. Okay, I asked that you estimate the delay between hop 3 and hop 4. Well, you might be thinking, hey, maybe I can calculate the average to hop 4 and subtracting the average to hop 3. Then, hey, that gives you the round-trip delay between 3 and 4, right? Hop 3 and 4. And if you divide it by 2, then you get the delay from hop 3 to hop 4. Okay, round-trip delay means going to a router, for example, hop 3, okay, and plus the delay coming back. So round trip is one way plus the return way. So round trip delay to hop 4 is delay to hop 4 and plus the delay from hop 4 and back. Okay. So can you calculate the delay from hop 3 to hop 4? Now the tricky part is this. Can you calculate the delay between hop 8 and hop 9? Okay. Well, you will see. You'll see once you start working on it. And we'll break open tomorrow's lecture with quiz number 6. The quiz is already posted on Slack. Of course, if you find time between now and tomorrow, feel free to post your solution. So tomorrow when we start doing the quiz, you guys can then see that Polly reading your solutions and see if any of your solutions is interesting. Okay, so Q1, Q2, a little bit trivial. It should be easy to answer. Q3 first might be a little bit easier. The second, getting the delay from hop 8 to hop 9 might be a little bit trickier. All right, so that's all for today. I'll see you tomorrow morning. Okay, so if you have any questions, feel free to type them up on Google Chat, YouTube chat, or on Slack. Either way is fine. And those who don't have questions, feel free to go. So go ahead and see if you can catch up with the next course a little bit earlier than usual. Well, actually just 1 minute earlier than usual. Okay. Okay. For those students, bye. Okay, thank you. Thank you, Catfish. Thank you, Zhongting. Thank you, Jia Hong. So what Polly is doing now is just to see, because in the video, the round trip delay to www.google.com is 30 milliseconds. That's kind of long. Let me do the trace route again, google.com, and see what is the delay like, round trip delay like today. Oh, 14届建物暑期营. That's a good question. I think you meant CDN, Content Distribution Network. Okay. So yeah, so ISP is Internet Service Provider. ISPs are usually telephone companies. Okay, the companies own the cables that's buried underground, the CDs. They are naturally the internet service provider because they have all these cables, okay, originally so that people can subscribe to DSL and then connect to the internet. And these telephone network company gradually expand that access network and now becomes ISPs. Okay, that's why Zhonghua Dianxin has a division, I think called HiNet. That is the internet part of Zhonghua Dianxin. CDN is different. Okay, CDN stands for content distribution. These companies typically do not own any of the cables buried underground each of the CDs. Okay, so they don't have access nets usually. What they have is they have data centers hosting the data. Okay, Google, recall that I mentioned one of these major content distribution network service provider. I think Akamai as well, Amazon as well these days. Dropbox, one can consider them one of these CDNs as well. Okay, so content distribution network. They are actually more end users like us.
what they are hosting in their data centers are a whole bunch of these servers. We keep data there. So Google, for Gmail service, keeps a lot of Gmail email servers there. So all our emails are stored there. Okay, but we all connect to the data center there, hosting all these Gmails. Now, these data centers nowadays have very good connection to the rest of the world, okay, although they don't have the access network. So once we connect to the data center, then from that data center, traffic can actually be related to other places. So CDN, quite different from ISP. To access internet, we pay to the ISPs. We don't pay the CDNs. But to get the data being hosted on the CDNs, we need to pay the CDNs. So that's their differences. ISP very well connected on the internet. CDN nowadays also very well connected on the internet. It's just that the cables they use to connect are different, and their reach to the end users also somewhat different. By the way, some of these CDNs are also becoming ISPs, trying to bury cables underground the major cities. Google, for example, has a division now, Google Fiber. Yeah, they are becoming an ISP, providing fiber-based access network to the end users. Interesting. Yeah. I guess also some of the ISPs will try to be a data content provider as well. Okay, content distribution network provider as well. Okay, so the roles of ISP and CDNs as 建物属情 are a little bit confused. They are becoming fuzzy and very similar, crossing over, each of them crossing over to the other direction. Okay, I hope that answered the question. Yeah, and you know what? It's 2:15. I'll just stick around for a little bit longer. You guys feel free to go. Okay. Who else are saying? Okay, Xiangbai and Zewei, Xuanhao, and Youyu. Okay, bye. Bye, guys. Okay, so I'll just end the stream now. Okay, choo-choo. All right, good. By the way, 14届届目属情, could you tell me your full name so that I can record your attendance properly? What is your name, the real name? If you can type it up, or if you are a little bit shy, feel free to direct message, DM me on Slack. That will also work. Okay, if you don't want people to know exactly who you are. Oh, okay. Wei Yuan, I see. Got it. Thank you, Wei Yuan. Exactly. The time to is the time at every hop being the time that passed to the next hop and back. Okay, so Keke, it would be easier if I try to explain with the mechanism. You see here? So for the output of traceroute shows, right, 1, and then the router's IP address, and then 3 delay messages, 3 delay estimates. So what are they? For the first hop, okay, what's being collected are these, the first 3 probes going to the first router and back. But the second entry there, okay, returning from the second router is actually this. The message traverse through the first because it's a route. So it needs to traverse through the first router to the second one and back. Okay, so those three values in the second row are the delay from the source, okay, the source PC over here, okay, to the second router, and then back to the source. Okay. Very good, very good. Okay. So you should be seeing that for the rows following the second row, the delay gradually longer because, hey, the physical route is longer. No problem, no problem. But it's not strictly longer. Why is the service time of caravan example being transmission delay, not processing delay? Okay. Very good question. Very good question. I guess you had a little bit of lessons about queuing and services. You know what? The caravan example, maybe I can go back to the side. Yeah, so the service time there, oops. Sorry about my display. The service time there is the time for that car to leave the toll booth. Okay. You see that on the internet, in order for a packet to leave a toll booth, the majority amount of time is to transmit the bits out of the interface. There is a processing time, but that is usually much, much slower. So in this example, think of it this. The processing time is almost like the toll booth lady there taking the money and handing over the ticket. But the car still need to drive through the booth. Okay, and think of the lady being, very swifty, very agile. Okay, so that is, taking not much time on the internet. But for the car to really drive through that booth takes longer time. Okay, so service time, in a way, I understand the question, Catfish. It should be the sum of processing time plus the transmission time. Okay. In this example, we only take into account the transmission time because we kind of assume that processing time is just negligible. As I mentioned in the formula earlier about the Nodal delay, the Nodal delay has 4 components. The processing part, very, very short. Oftentimes we neglect the processing time. But in the caravan example, I understand usually the Whole Foods ladies, okay, how agile they are can be quite diverse. Okay, these days in Taiwan highway, we just use the scanner system. I mean, I don't think do we still have these men attendant human labor toll booths? I haven't been going to those toll booths lately. So think of these toll booths are now all automated. Okay, there's no human there causing a long processing delay. Okay, I hope that answered the question, and sorry for the confusion. The service delay should be both processing and transmission, but processing delay, it's on the internet oftentimes very, very short. We kind of ignore it. Does the entire caravan stand for a packet? Well, that's a good question. It really, let me see. Yeah, I think the caravan there stands for a sequence of packets that are sent out at once. Okay, so the first toll booth will be like the first router. So usually from a user, when you send traffic, you send a whole bunch of packets back to back. But as they travel through these routers, they might mix with other cars in other caravans. Okay,
And the delay of handling one car might be a little bit longer. The caravan might be stretched. Okay. Yeah, so try to think of a caravan as a series of packets. Okay, and that's what I actually meant with the example, a series of packets. So they might get stretched out, especially for the cases where the propagation delay is short. Now you see. So they get stuck in the queue in the earlier toll booths. Some of the later cars get stuck in the earlier toll booths because the transmission delay is a little bit longer than the propagation delay. All right, good. I had a feeling that YouTube live stream this semester is different from previous semester. The delay was very short last semester, but for this semester, I can feel that the end-to-end delay from me to you quite long. That's why when I ask if you have questions or do simple things like saying okay, it takes a long time for you to feedback. So that also shows in the time you manage to post a question, because there's a delay that you hear about it, and plus the thinking delay, and then you post the question on the YouTube live chat. Very interesting. It's a challenge. We'll see how. Okay, so maybe next week I will, or actually tomorrow, I'll try to do something like I test and figure out how long the end-to-end delay is from poly to you, so that I get a better chance how much I wait until you can pose questions. All right, so thank you for those stayers. Okay, I guess you get to hear more about these things that other students get confused about. Good. Oh, I actually see students posting solutions to quiz 6 already. Ooh. Oh, it's from team 1. Okay, team 1, very good. Like that. Good. So see you tomorrow. Okay, I'll end the stream now. Bye.